Curves defined by parametric equations. Consider the following graph. Notice that due to the shape of this graph, it is not possible to list y as a function of x. And this is because if you draw a vertical line, you'll see that the vertical line intersects the graph at multiple points. This means that we cannot express y as a function of x like we normally would. In such cases, it is sometimes possible to express this curve by using something called parametric equations. Basically, what happens here is that the x variable can be written as a function of a third variable t, and the y variable can also be written as a function of that third variable t. And when x and y are both given as functions of this third variable, the third variable t is called the parameter, and the equations x equals f of t and y equals g of t are called the parametric equations. Now each value of t determines a point xy on the curve. So as t varies, or as t changes, the point xy is going to vary and trace out the curve that we typically call a parametric curve. So we don't usually refer to these as graphs or as functions. We tend to call them curves. The parameter t does not necessarily represent time, and we can actually use any other letter besides t, but in many cases t does represent time, and it's one of the reasons why t is our most common parameter. As you progress through math classes and physics classes, you will find that parametric equations are extraordinarily useful in describing real phenomena. Let's take a look at a simple example. So in the first example here, we would like to sketch and identify the curve defined by the parametric equations x equals t squared minus 2t and y is equal to t plus 1. And there are a few methods for sketching this curve, but we're going to take the most basic approach, which would be simply choosing values of t and then plugging them into both of these equations to get the values of x and y. So let's start by choosing a random value for t. Suppose t is equal to negative 2. If this is the case, then x is going to be negative 2 squared minus 2 times negative 2. And this is 4 plus 4, which is equal to 8. Y will be equal to negative 2 plus 1, which is negative 1. And so this means that when t equals negative 2, it corresponds to the point 8, negative 1. Let's do this for a few more values for t. Suppose t is equal to negative 1. X is going to be negative 1 squared minus 2 times negative 1. And this is 1 plus 2, which is equal to 3. The y variable will be negative 1 plus 1, which is equal to 0. And this gives us the point 3, 0. What if t is equal to 0? Well, x is going to be 0 squared minus 2 times 0, which is 0. And y will be 0 plus 1, which is 1. And this gives us the point 0, 1. Now, we can continue doing this for as many values of t's as we like, but usually when you do several values of t, you will begin to see what the shape of the graph is going to look like, or the shape of the curve, I should say. Let's go ahead and take a look at a table that has these values and a few more. So here you can see the 3 points that we determined, 8, negative 1, 3, 0, and 0, 1. And if we continue with allowing t to equal 1, 2, 3, and 4, we obtain a few additional points. Let's graph these points. So the first point when t equals negative 2 is the point 8, negative 1, which is this point right here. When t equals negative 1, we get the point 3, 0. When t equals 0, we get 0, 1. T equals 1 corresponds to negative 1, 2. T equals 2 corresponds to 0, 3. T equals 3 corresponds to 3, 4. And finally, when t equals 4, that corresponds to the point 8, 5. So if I label these, t equals -2, t equals -1, t equals 0, t equals 1, t equals 2, 3, and 4, you can see that as t gets bigger, it appears that we are tracing out this curve. And this curve does appear to be a parabola. And one thing about parametric equations that is quite different from other graphs is that there is a definitive orientation to this curve. In other words, as t increases, the curve moves in this direction. And this is referred to as the orientation of the curve. Now, there is another way that we can come up with the graph of this curve, and that is by eliminating the parameter. So let's notice that if x is equal to t squared minus 2t and y is equal to t plus 1, in the second equation, we can easily solve for t by subtracting 1 from both sides. In doing so, we get t equals y minus 1. And then from there, we could take this expression and substitute it in for t in the first equation. Doing so gives us x is equal to y minus 1 squared minus 2 times y minus 1. Now, if we multiply this out, we're going to have x equals y squared minus 2y plus 1 minus 2y plus 2. And this gives us y squared minus 4y plus 3. Now, another thing that could be done here is we can complete the square on this expression here. And we can do that by simply moving the plus 3 a little bit farther out here. And then to complete the square, we need to take half of this number and square it, which is 4. And I'm going to add 4 there, and then I'll subtract 4 out here. And this allows us to express this as y minus 2 quantity squared minus 1. And this falls into the category of curves x is equal to a times y minus k squared plus h. And this is a parabola with a vertex at the point hk, and it's going to open left or right. And it opens left or right depending on the value of a. If a is positive, it opens to the right. If a is negative, it opens to the left. In our case, the number a in front here is equal to 1. And so this is going to open to the right, and the vertex is going to be -1, +2. So for the vertex, you have to take the value here, that's your x coordinate, and then the opposite of this value is your y coordinate. And you can see that this is consistent with the graph that we have. You can see that x equals -1, y equals 2 is this point right here, and we have a parabola opening to the right. Now, that doesn't fully give you the parametric curve because, again, the parametric curve also has orientation. So even if you eliminate the parameter to figure out what the curve is going to look like, you need to at least plug in a couple of values for t to see which way is the orientation. Before we go on to our next example, let's look at a slight change to the previous example. Suppose you had been asked to sketch the graph for the same parametric equations, but now they restrict your domain for t. So they're basically saying here that you are only allowed to plug in values of t between 0 and 4. So if we bring in the table that we just looked at a few moments ago, we'll go ahead and cross out the first 2 lines of this table. Because if we're only looking at values of t between 0 and 4, we would only be concerned with these points. Now what this is going to do is basically give us the graph of the same parabola that we had a moment ago, except that it's going to be finite in nature. In other words, it will have a beginning and an end. So if we go ahead and plot these points, when t equals 0, we have the point 0, 1. T equals 1 corresponds to negative 1, 2. T equals 2 corresponds to 0, 3. T equals 3 corresponds to 3, 4. And finally, t equals 4 corresponds to 8, 5. Now the important thing here is this point corresponded to t equals 0, and this point corresponds to t equals 4. So this point here is the beginning, and we are going to trace out the curve in this direction, and the point over here is the end. And it has a very definitive orientation once again. So in general, when given parametric equations x equals f of t and y equals g of t, where t is between two values a and b, this curve will have an initial point at f of a and g of a, and a terminal point at f of b and g of b. So for example, if this is our curve between t equals a and t equals b, this point here, which is the initial point, and by the way, we know that because of the orientation of this curve moving in this direction, this point would be the point f of a, g of a, and that of course corresponds to t equals a. And the point over here is the terminal point f of b, g of b, and that corresponds to t equals b. So for our second example, we ask what curve is represented by the following parametric equations: x equals cosine of t, y equals sine of t, where t is between 0 and 2 pi. Now again, we could make a table of values for t, x, and y, but let's remember from trigonometry that cosine squared of t plus sine squared of t is always equal to 1. And then cosine squared of t can be written as cosine of t quantity squared. Sine squared of t can be written as sine of t quantity squared. And now if x is equal to cosine of t, we can plug x in here for cosine of t. And if y is equal to sine of t, we can plug y in here for sine of t. And if we do that, we get x squared plus y squared is equal to 1. And we should recognize that this curve is what we call the unit circle. That is, it is a circle centered at the origin, 0, 0, and the radius of this circle is equal to 1. So I'll just remind you that the unit circle is a circle that looks like this. It is centered at 0, 0 and has a radius equal to 1. And you'll notice that I went ahead and showed you all the details of this curve. So for example, when t is equal to 0, that corresponds to this point here. And that's because if t equals 0, x is going to be the cosine of 0, which is equal to 1, and y is going to be the sine of 0, which is equal to 0. And that gives you the point 1, 0. So that is this point right here. And that is the beginning of the curve because that is our smallest t value that we are allowed to plug in. If we move around here, plugging in t equals pi over 2, let's say, is going to give us x equals cosine of pi over 2, which is equal to 0, and y is equal to sine of pi over 2, which is equal to 1. And that, of course, gives us the point 0, 1, which is this point right here. Now, what's nice about that is it not only does it give us a couple of points, but it also tells us that we are moving in this direction. So it begins to give us the orientation of the curve. Well, if you continue by plugging in t equals pi, you will get the point here. So we continue with that same orientation. T equals 3 pi over 2 gives us this point here, which means we are continuing with that orientation. And finally, when t equals 2 pi, we are back here where we started, and that is the end of our curve because t only varies between 0 and 2 pi. So basically, this gives us the unit circle with counterclockwise orientation and a single revolution, right? Because the beginning and the end are at the same point, and we did trace through this only one time between 0 and 2 pi. So the parametric equations that you see here are often called the parameterization of the unit circle. And this is important because the unit circle is important, and anything that is important in mathematics is important to understand how to parameterize that thing. So here is a slight play on the last example. What curve is represented by the given parametric equations? X equals sine of 2t, and y is equal to cosine of 2t. Well, again, we know from trigonometry that sine squared of any angle, including 2t, plus cosine squared of the same angle is always equal to 1. But sine squared of 2t is the same as sine of 2t, quantity squared, and cosine squared of 2t is cosine of 2t, quantity squared, is equal to 1. Now, x is equal to sine of 2t, so we can plug x into here. And y is equal to cosine of 2t, so we can plug y into here. And in doing so, we get x squared plus y squared is equal to 1. So once again, we have the unit circle. But is this the exact same curve as the previous curve? Well, it seems to be, because we get the same curve, right, the unit circle, and we also have the same values for t. T varies between 0 and 2 pi. But let's take a closer look. So let's start by plugging in t equals 0. When we plug in t equals 0, x is going to be the sine of 0, which is 0. Y is going to be the cosine of 0, which is 1. So that is the point 0, 1. Now, the next value that I'm going to plug in, normally I would do pi over 2, but I'm going to do pi over 4 in this case. And the reason is really simple. When I plug in pi over 4, x is going to be sine of 2 times pi over 4. And see, that gives us the sine of pi over 2, which is 1. And y is going to be the cosine of 2 times pi over 4, which is the cosine of pi over 2, which is 0. And this gives us the point 1, 0. So let's start to think about what we have here. When we plug in t equals 0, we get the point 0, 1, which is this point here. So this is our initial point. When t equals pi over 4, we're getting the point 1, 0, which is here. So even though we know that this is a unit circle, it does appear from these 2 points that we are orienting in this direction. But we can keep on going here. We can plug in another value for t. Let's say we plug in t equals pi over 2. In this case, x will be the sine of 2 times pi over 2, which is the sine of pi, which is 0. And y will be the cosine of 2 times pi over 2, which is the cosine of pi, which is negative 1. And this gives us the point 0, negative 1, which we can clearly see is this point on the curve. And so we are continuing to trace out the unit circle. But again, this is all the way up to pi over 2. So what you're going to find here is that if you continue to trace this, at 3 pi over 4, you'll be at this point here, and at pi, you will be at this point here. So when you go from 0 to pi, you are going to trace out counterclockwise 1 full rotation. But then we start all over again, because remember, we are going to 2 pi. So if 0 to pi traces 1 full rotation here, then when we go from pi to 2 pi, it's pretty easy to show that we will just get another rotation. And one way to indicate this is you could just do sort of a parallel tracing to show that you are going around one more time. Or there's actually a better illustration of this that I can bring in here. And so this shows that we are tracing out the unit circle here. So the red curve here is the unit circle. And then this tells us that when we start here at t equals 0, we are going to trace around this curve from 0 to pi. It takes us to here. And then from pi to 2 pi is going to take us around one more time. So although the curve is the same in terms of the set of points as the last example, the tracing of the curve is different, both in direction and also the fact that we trace through this circle 2 times as compared to only tracing through the circle 1 time in the previous example. And this is why parametric equations are so valuable, because they can distinguish between these small differences between the curves. In the next example, we're asked to find the parametric equations for the circle with center HK and radius R. So here I have the graph of a circle whose center is at HK and whose radius is R. Let's suppose that we choose a point on the circle here, and we'll say that the coordinates of this point are X and Y. Now notice that I can draw a right triangle here, and I can find the length of this side here by taking the X coordinate of this point and subtracting the X coordinate of this point. And of course, that's just going to be X minus H. And I can find the length of this side here by doing the same thing. I'll take the Y coordinate here minus the Y coordinate here, which is going to be Y minus K. And then now we have a triangle that is actually a right triangle, and therefore we can use trigonometry. So if we suppose that this angle inside the triangle here is t, then what we know is that the cosine of the angle t is equal to the adjacent side, which is x minus h, divided by the hypotenuse, which is r. And the sine of the angle t is going to be equal to the opposite side, which is y minus k, divided by the hypotenuse, which is also r. And so now that gives us two equations involving x, y, h, k, r, and t. And now if we just solve by getting rid of the fraction here, we can say that r cosine of t is equal to x minus h, and r times sine of t is equal to y minus k. And then finally, to solve for x here, we get x is equal to h plus r cosine of t, and solving for y here, y is equal to k plus r sine of t. And these are the parametric equations for a circle with center at 0, 0, and radius, with center at HK and radius equal to R. What I was going to say is that notice now if we were asked to find the parametric equations for the unit circle, all we would have to do is recognize that the center is 0, 0, which means that h equals 0 and k equals 0, and the radius would be equal to 1. And if we plug those quantities in, we would get x is equal to 0 plus 1 cosine of t, and y is equal to 0 plus 1 sine of t, or in other words, x is equal to cosine of t, and y is equal to sine of t, which of course is the first set of parametric equations that we use to describe the unit circle. In the next example, we want to sketch the curve with parametric equations x equals sine of t and y equals sine squared of t. And the whole reason for doing this example is that you get a very unique tracing pattern when you trace this curve. So let's first talk about what the curve would look like. So if x is equal to sine of t and y is equal to sine squared of t, you certainly could plug values of t in and find points x and y. But actually it's much easier to just recognize that if x is equal to sine of t, or if sine of t is equal to x, you can express y as sine squared of t, which is the same as sine of t quantity squared. And now if x is equal to sine of t, we can put x in here replacing sine of t. And if we do that, we end up getting the equation y equals x squared. And of course, we know that y equals x squared is a parabola. In fact, it is the basic parabola, which I'm sure everyone remembers, looks something like this. However, that is not what these parametric equations produce. So let's try to find out why this is not the case. Now let's remember that for any value of t, the sine of t is always going to be a number between 1 and -1. And therefore, sine squared of t is always going to be a number in between 1 and 0. And this is because when you square something, it can never be negative. So if sine of t is always a number in between 1 and -1, and if sine squared of t is always a number between 1 and 0, let's recognize that x is sine of t, and so this means that x would have to be a number in between -1 and +1. And then further, let's recognize that y is sine squared of t, and so y would have to be a number in between 0 and 1. So if you look at the graph of the parabola here, here is x equals -1, x equals +1, and here is y equals 1. We can see that we are not going to get this portion of the graph, nor are we going to get this portion of the graph. Because again, x must always be a number in between -1 and +1. So we're only going to get this section of the graph. And notice that that's also consistent with the fact that y has to be a value between 0 and 1. But then what does the tracing look like? Well, for that, let's go ahead and plug in a couple of values for t. So if t is equal to 0, x is going to be sine of 0, which is 0, and y is going to be sine squared of 0, which is 0. So when t equals 0, we get this point here. Now, what about when t equals pi over 2? If t is equal to pi over 2, x is going to be the sine of pi over 2, which is equal to 1, and y will be sine squared of pi over 2, which is 1 squared, which is also 1. So that's the point up here. So this corresponds to t equals pi over 2. So it does appear that we are tracing the curve in this direction. But what happens then? So between t equals 0 and t equals pi over 2, we trace the curve up here. But what about the rest of the curve? Well, what's interesting is when you plug in the next value for t, the next easy value for t, which is t equals pi, x is going to be the sine of pi, which is 0, and y will be sine squared of pi, which is also 0. So the point is, when we plug in t equals pi, we are back at this point again. So what happened here is we traced it from t equals 0 to t equals pi over 2 in this direction. But then from t equals pi over 2 to t equals pi, we're coming back the other direction. And in fact, if you continue it from there, we're going to move up to the point -1, 1, and then we'll move back to the center again. So what happens is you get this oscillation that occurs here. And I'll go ahead and bring in a little better picture just for clarity. So again, what is happening here is we have t equals 0 corresponding to the origin here. And then when t moves from 0 to pi over 2, we trace the curve in this direction. When t equals pi over 2 to pi, we trace the curve in this direction. From t equals pi to 3 pi over 2, we go in this direction. And finally, from t equals 3 pi over 2 back to 2 pi, we come back this direction. And we just continue to oscillate back and forth. So the really cool thing about parametric equations is that they can take regular graphs, such as the graph of a parabola, and they can alter the domain and range so that you only get a piece of that graph. And then in addition, you can have this sort of oscillation back and forth indefinitely. And this simply cannot be described by using regular, rectangular, or Cartesian equations, right? So when we talk about the curve y equals x squared, these are called the rectangular equation or the Cartesian equation for that curve. And of course, y equals x squared describes some of what is happening here, but it does not describe the oscillation, it does not restrict the domain, etc. So parametric equations are really useful in that they can provide a lot more detail about the graph than the simple Cartesian equation can provide. And for our final example of a parametric curve, we're going to talk about the cycloid. So the cycloid is a curve traced out by a point P on the circumference of a circle as the circle rolls along a straight line. So think about something like a car tire or a bicycle tire. If you start to rotate that tire forward, the point on that tire or the point on that circle is going to make this particular pattern. So let's imagine if we have a tire sitting on the ground like so, and we're going to have the point at the very bottom of the tire. When you start to roll this tire forward, so when this tire starts to move in this direction, this point is going to move in such a way that it gives you this kind of a shape. Okay? Now you can imagine that this is going to happen by thinking about what's going to happen when this tire rotates halfway around. So let's call this point A on the tire, and we'll call this point B on the tire. When I rotate this tire forward so that now point B is on the ground, then point A is going to be where point B is. So a picture of what that tire would look like halfway through its rotation would look something like this. And so now point A is up here and point B is down here. And all during that time that it's rotating, point A on the tire is traveling in this path. And then when you rotate the tire halfway through another rotation, it's going to come back down to be on the ground again. And so that's what's happening here when you look at the cycloid. And just as a note, what I'm going to do is put an animation link in this video so that you can click on it and watch the cycloid being formed. It's a really interesting video. Just look down in the description and click on that if you want to check that out. And here are the parametric equations for a cycloid. So R represents the radius of the original circle, and theta represents the angle through which the tire is rotated, and X and Y represents a point on the curve. So we have X is equal to R times the quantity theta minus sine of theta, and Y is equal to R times the quantity 1 minus cosine of theta. And I won't go through the derivation process here, but there's going to be some interesting applications using a cycloid in the upcoming video lessons. And one last thing, most instructors would not have you memorize the parametric equations for a cycloid, but you definitely want to check with your instructor to make sure that's the case. And that concludes this video lesson.